Hello everyone, welcome to the 3D scanning and motion capture lecture. So today is the first kind of official actual lecture where we talk about the content of 3D concepts and sensors. So remember last time we gave a very brief introduction about some high-level topics. So we talked about motion capture, like here we saw this video from Avatar, where you essentially had to wear mocap suits in order to be digitized. We also talked a little bit about capturing 3D geometry. Here we saw some Matterport scans that were in indoor environments that resulted in some 3D models with textures on top of it. We also talked about some applications outdoors where you had multiple images and you wanted to also reconstruct the respective 3D geometry around it. So today we want to actually dive a little bit deeper. And first we wanted to start with understanding what 3D actually means. So I've been talking about this, all the time, and you probably heard it also all the time. But probably if you ask different people, they have very different understanding what 3D is, right? And we can even simplify it a little bit more. We can say, well, let's start with what 2D is. And in computer science, when we're talking about 2D, we most of the time talk about images. We talk about an array of pixels that is arranged in 2 dimensions, right? So for instance, if you implement this in your favorite programming language, which is of course C++, then you have an array, right? And this array has 2 dimensions, and then at every I and j location, you can access a respective color value, right? And if you want to store an image now in this 2D array, what you do is you have a process which is called rasterization. So in this process, you have this original image here. This is actually a vector graphics, and this one you can basically, you just have this virtual, or you have this grid on top of it, right? This is this 2D set arrays of pixels, and then for every pixel, you're going to store an RGB value. An RGB value in this case is just 3 channels. You have a certain bit depth, typically it's 8-bit, but could be higher per channel. But this RGB value is stored on the respective pixel location, and then you have kind of this, as a result, you get this pixelated output. And this is typically when we're talking about images, and this is what a 2D representation of an image on a computer looks like. Nothing fancy, everybody probably knows that. If you want to have higher resolution images, you have to store a larger 2D array, right? And this is typically what you're getting when you're taking pictures from a webcam. You're checking out from a camera in general. You're probably checking out, what's the resolution, and this determines the quality in the end in terms of how to avoid these pixelization artifacts, and you can get a better approximation of the real world that is captured with the webcam. So nothing fancy here. I'm going to ignore a couple of 2D representations, right? I already mentioned there's things like vector graphics as well. That's maybe not part of this course, at least not for the time being. We're going to just think about a 2D image right now as a 2D array with RGB colors at every pixel location. And of course, you can do the same thing in 3D. So in 3D, you can just say, well, we're just gonna have a 3D grid, three-dimensional array right now. And these ones are not pixels anymore, but voxels. And voxels is a volumetric representation where you now have this 3-dimensional array, right? So in this case, if we are looking here, right, we have this cube here. It has a certain resolution in X, Y, and Z direction. And in each of these voxels, we can store a certain values. Now, it's not just in 2D where you have an RGB value. In 3D, there's different things you can actually store inside a voxel. So the standard thing what you store is an occupancy grid, actually. So in this case, every voxel can just store, is there a surface or is there no surface? And this is called a binary voxel grid, right? So you literally want to just indicate, is there something there or is there nothing there? But then you can also go and make this a little bit more complicated. You can say this is probabilistic, so you kind of say, it's partially occluded and partially occupied the voxel, and then you just store a floating value. But there's other ways to it too. But on a high level, the idea of a voxel grid is simply an extension of an image in 2D where you have pixels. You have just the 3D analog of a pixel is now a voxel, and this results in a 3D array where you store the values of these respective voxels. Again, nothing complicated, pretty straightforward so far. But now you can extend this a little bit, right? And instead of just storing an occupancy, you can also go ahead and store, for instance, voxel colors, right? So now for a voxel, you would store, is it occupied or is it not occupied? And if it's occupied, you also store an RGB value that indicates a color. And colored voxels is essentially what people do in Minecraft, right? It's a very popular example. So you have this kind of blocky, voxelized world, and that stores voxels and the respective color values. And similar as in 2D, what I mentioned, if you want to have higher quality surfaces in a sense, you have to increase the resolution here in order to get higher quality or a better approximation basically of the actual underlying surface. And we'll get to this in a bit, whatever the surface actually is. But so far we have heard about this extension now, right? So we're starting in a 2D, we're starting from a 2D image, and now we're extending it to 3D, and now we're having voxels instead of pixels. Okay, but that's of course not the only representation. There's many other 3D representations. There's things like point clouds. This is something you will see often in this course. We will actually cover a lot of the things that come with point clouds. So the point cloud is very straightforward. This is just a linear array, and in this linear array, you're storing three-dimensional points. Each point has an x, y, and a z coordinate, and this is your point cloud. Now, in addition to the point coordinates, you can go ahead and also store associated attributes. So you can store a point color, a point normal, and so on. There could be other attributes too, but for now, this is probably what we're gonna need. Points is in a sense not a surface representation, right? So points is only points by definition, and it doesn't by itself store a surface. So often the point clouds we are getting from raw measurements of a sensor. So we'll see this in a second how we get those. But there's no surface definition, right? There's nothing defined that says, oh, how do you connect these points? And there's no inter and extrapolation between the points. But often the points are input to algorithms that then generate a surface as output. We'll discuss these methods actually in this lecture quite in detail. How do we go from a raw point cloud that a sensor gives us, for instance, a laser scanner, and then how do we get to the respective surface as an output? But for now, point cloud, very straightforward. You just have a linear array. In this case, we are in 3 dimensions, right? So we have x, y, z coordinates for every point, and possibly we have some attributes such as colors and normals. Yeah, so very importantly right now, what you can already see in terms of like what's represented, if you're going back quickly, so we had these voxel grids, right? They actually require cubic storage because here you're storing values not just on the surface, but everywhere in 3D space. Whereas if you have points are kind of this sampling of the surface. So you can abstract an abstraction where you have a bunch of, for instance, measurement points that sample the surface, but this one is just linear in terms of complexity of storage, right? So voxel grid cubic, this one is linear. But one of them actually is stored everywhere, and this one is just stored at a bunch of sample points on the surface. So one thing what is also important when we're talking about points, so points only store a value for sample points on the surface. They basically give you not so much information about stuff that is not on the points, right? So for instance, if you're going ahead and having a point cloud with a real sensor, so let's say you take a laser scanner that gives you a bunch of points from a certain view, it only tells you a few sample points where a surface is. But for areas where you don't have any points, you have no distinction whether there was actually a surface point or no surface point. So you just don't know in unknown regions. Whereas in a voxel grid, you would have that. A voxel grid would tell you, oh, there's nothing there. Whereas in a point cloud, that's different, right? In a point cloud, you only have these samples, this approximation of the surface, but it doesn't tell you anything in regions that you haven't observed yet. Okay, now we have voxels, we have point clouds, and now if you want to have actual surfaces, we can go to meshes. And meshes is typically something that is used heavily in computer graphics for video games or for movies, right? These are actually surface representations. These are polygonal meshes, meaning that you have this mesh, right? You have these vertices that define the corner points of each face. Then you have the edges that connect the vertices, and you have the faces that actually define the surface, then, right? So you have vertices and faces, and what's often the case is that these are actually triangular meshes. There are certain reasons from a modeling perspective why triangular meshes are often used. It's just a lot easier to generate. But there's also many other methods that say, oh, we want to have quad dominant meshes or quad only meshes. But for the most part in computer graphics, people actually use triangle meshes. It's also basically what modern graphics cards take as input in order to render and rasterize the respective outputs. So, video games and graphics cards, what they do is they take these meshes as input, and then they generate the respective outputs in 2D. So they rasterize it and generate images out of these. One thing is, like these polygonal meshes, what's important from a surface modeling standpoint, these are piecewise linear, right? So meaning that you just have a face, and there's just a kind of a linear interpolation between those points on that face, right? There's no curvy face, so to say, in polygonal meshes. But what we can have attributes. Typically, they're stored in the parametric spaces, but they could also be stored on a texture basis, right? So we can have colors, we can have surface normals, we can have textures, and so on. So these things actually get you a little bit more life into it, right? So these are like untextured surfaces here. But if you actually take all these attributes and you add a little bit of texturing and lighting, eventually you get images that could be rendered like these ones here, right? So these are high quality renderings from surface definitions with polygonal meshes. And here, like, graphics methods have been used. On the left-hand side, this is actually a ray traced version. This is a rasterized version on the right-hand side. And these ones are being generated with, from these representations with modern rendering techniques. So we're not going to go into the rendering techniques. That would be a question of computer graphics, like how to do this efficiently, how to make the rendering look pretty. But what we are really interested in is, for instance, how do we obtain these surfaces? How do we obtain the 3D structure, the vertices, the faces, possibly even color normals and textures, right? And for that reason, it is very important to understand what the representations here are, right? And it's actually not so straightforward to go from a, let's say, laser scan, unstructured point cloud, to go to a good high quality mesh at the end of the day that you can, for instance, use in a video game. So this is quite challenging still. But there's not only polygonal meshes the way we just described it. And one of the limitations there is that these are actually piecewise linear, right? So when I mentioned this, you're going to get, like, if you look, there's like a face, right? And then you have this crease kind of when the next face comes. This is, by the way, the reason why people store surface normals. So they're trying to basically have a higher order approximation of the surface with the normals that can be then later used to have kind of like fancy shading effects and so on for the rendering. Again, we're not going to go too much into it. What's important is we have these piecewise linear versions. This is our polygonal mesh. And you can expand this and say, well, we don't want to have it piecewise linear. We can go also into parametric surfaces. And this is heavily used in the movie industry, also in the car industry, actually, in CAD modeling software. You would also use parametric surfaces, and the idea is similar to polygonal meshes, except that now these vertices, they are being turned into control points, and these control points, they define a higher order surface. So splines, Nurbs, or subdivision surfaces are precisely that. So what you have here, we have a grid of control points. Again, these are like vertices in a mesh, except there's now a higher order approximation of the surface. So for instance, a cubic B-spline would have a couple of control points here, and then there's a cubic surface defined by these spline control points. And that has certain advantages. Now we don't have these creases anymore between neighboring patches or faces, in this case, in a polygon mesh. But here you're actually having a continuous C1 or C2, depending on what kind of order the parametric surface is. You can kind of approximate the surface with this higher order function, and then you don't have these hard creases at this point anymore, meaning that you get a smoother representation of the surface, and for certain applications that is very desired. So for instance, here's an example from Cherry's Game. This was a Pixar short movie in the 90s, and they use subdivision surfaces as one of the first movies that used it as a production chain. and this later became like the basis for all like the Pixar animation studio movies like Toy Story and so on. And they heavily built on these techniques that the researchers there built up for this Jerry's Game short movie, where they demonstrated this take one of the first time. And it has certain advantages when you do modeling, because you have these smooth surface approximations that give you kind of nice normals, which in turn give you good shading when you render the images. So we don't want to go too much into detail about, you know, like how to, again, the rendering is not so important right now for us. But what is important for us, that we could possibly think about using like parametric surface representations also when we're doing reconstruction of surfaces, right? So for instance, when you have a point cloud, you could very well imagine that you wanted to fit these parametric surfaces to it. And we'll talk a little bit about later when I say fit to it. Most of the time this means that there's a nonlinear optimization problem that essentially optimizes for, in this case, you would optimize for the control points, such that the input points that are being scanned are well approximated enough. And then the surface would extrapolate kind of the points. Okay, so what's very important right now is what we have. We have polygonal meshes that are piecewise linear, and now we have parametric surface that can have higher order representations. Typically in practice, people use degree 3 here, so cubic is very common. It has a couple of nice properties for the surface normals. So basically, cubic gives you continuous normals, and it's a desirable property when you want to animate these surfaces to get nice shading at the end of the day. Okay, but yeah, that's probably it right now for parametric surfaces. Again, there's specialized courses that only deal with these kind of representations, but we're gonna probably leave it at this for now, and we're gonna move on with a few other representations. And you might ask, what's left? So we have voxel grids, we have meshes, and we have parametric surfaces. But there's also a thing called implicit surfaces. And actually, implicit surfaces is very closely related to the voxel grids. And the idea of implicit surfaces basically means instead of storing in a voxel grid an occupancy value, you can store in an occupancy in a voxel grid. You can store a floating point value per voxel that tells you how close are you to the respective surface. So here's an example of this. So let's take this grid here. Let's just assume these are like 3D voxels. I understand this is in 2D, but just imagine this was in 3D. And now what you can do is, by the way, this works in 2D as well. But now what you can imagine is, like each of these values in here, they tell you how far away are you from the actual surface. So for instance, if you have a 1 here, that tells you the distance to the surface here is 1 voxel away, right? You don't know where, but it just tells you it's 1 voxel away. And if you look at the neighbor here, okay, here it says 0.4, it tells you now, oh, it's only 0.4 voxels away. So you know, oh, there's kind of this gradient, so you know, oh, if I go from 1 to 0.4, you know, kind of in this direction here, there must be coming a surface, right? Because these distance values, they're becoming smaller and smaller. And at some point, what happens is there's a 0 here, or something that is close to 0, that tells you now, oh, here's a surface, right? This is called the isosurface. This is where the value of this implicit function of the sign distance field is actually approaching 0, or it's a 0 crossing where you have 1 voxel that was positive and 1 voxel was negative. Right? So here it's positive and then here it's negative, so you know, oh, there must be a surface in between. This is kind of how a distance field or a sign distance field defines the surface, and we call this an implicit surface because now we have no explicit value that tells you, oh, there's like a vertex or a face. The only thing you're going to have right now is saying, hey, there's a distance value there, and it tells you how far away you are, and you kind of have to find a way how to actually extract the explicit surface out of it, and there's many methods for it. So one thing we're going to look at is marching cubes. That's a way to get a surface out of it. And now there's a lot of different variations of these kind of things, of these implicit surfaces. So sign distance fields is only one of the ways. And the idea of the sign distance field is kind of what I said. It says the distance field tells you how far away from the surface you are. This is the distance value. And the sign tells you whether you are in front or behind the surface. But there's, again, more variations. I'm not going to go into all of them. We're going to talk about this in detail a little bit later. The sign can also mean it's inside or outside the surface. It could be meaning front or behind. It could mean inside or outside. It could even also mean that it's known versus unknown, but that we will discuss later about. The most important thing right now, what you have to remember is we have a distance field. These distances are stored on a per voxel basis. They tell you how far away you are from the surface. And based on this representation, you can extract an explicit surface like a triangle mesh out of it in order to have an explicit representation. Right. Question is, why do we do that? Well, it turns out like these distance fields or these implicit functions or surfaces, they are actually quite good when it comes to reconstruction. So for reconstruction-based problems, we will see a couple of methods that use these heavily in the method in order to obtain a high-quality surface from possibly a noisy point cloud. The other thing what you see on the slide here is a thing called truncated sign distance. So the truncation just means we just don't care a certain value anymore when you're too far away from the surface. So right, for instance, here it like just goes to 1, and everything else that is further away is also 1. And this truncation can be set also to an arbitrary value in a sense. It has certain implications when we come talking about reconstruction, but for the time being, you just have to know that this kind of exists. How and where we're going to use it, we'll talk about it a little bit. Okay, often you see this visualization of these distance fields. They look something like this, right? So here red is, for instance, very close to the surface, and blue would be further away. This is one way to visualize it. In 3D, that's not always so easy to visualize it, because you obviously have a volume, right? And then you have some way of like either slicing through the volume or having some sort of volumetric rendering. Okay, but I think conceptually it seems still pretty straightforward, right? So what we have is we have kind of a voxel grid. Every voxel stores a distance value, tells you how far away from the surface you are. Could have a sign value that might mean that it's inside the surface or outside the surface or behind the surface, depends a bit how you created it. And then we might have things like truncations that tell you at some point where to cut off the distance field. Okay. I wanted to make a very quick side note because I know there's a couple of lectures. I'm teaching some of them, especially in the deep learning context. I wanted to quickly remind everybody what implicit as a function means mathematically. So when you have an explicit function, then you just say f of x, you feed in x into a function f, and you get a value as an output, right? If you're having an implicit function, then you have something like this, right? So like x squared plus y squared minus 1 is equal to 0, right? So this one means you can't just put a value in, but you have to reconstruct the respective explicit representation afterwards, right? By the way, this is just a circle. But this circle here is defined essentially by this equation. It says, oh, it defines where all of these values here have to fulfill this property, and then they're part of the respective curve here. And this works in 3D in the same way. And this implicit function that we just had, the sign distance field, is exactly an implicit function because here the surface is not explicitly defined, but you have to reconstruct it. So it just tells you, oh, the surface is that far away from my current voxel, but then later you need a method to figure out how to actually get the surface in an explicit representation out of it. So this is very important. The reason why I'm mentioning this right now, when you, for instance, searching and doing some literature research for implicit surface representations, there's a bit of a confusion right now in the literature. So in neural networks, and I'm going to do a quick detour here, in neural networks there's these multi-layer perceptrons, and you can actually encode a distance field in a multi-layer perceptron. And the way you would do this is you have kind of a neural network. You're feeding on an x, y, z coordinate here as input, and the network gives you an SDF value as an output, as a distance value as an output at this specific query coordinate. So in a sense, the neural network here, there's no learning going on. This is not a learning-based method. This is just a method where you can kind of abuse a neural network in order to replace the voxel grid data structure with an MLP. I just wanted to make sure that sometimes these ones are being called implicit functions or implicit representations. And that technically is wrong, because this is still a function where you're feeding an x, y, z coordinate as input, and you're going to get an SDF value as output. So this is an explicit function, right? It's f of x. X is this here, y is the output, and f is the network here. And The reason why people confusing it is because often these things, they encode sign distance field, whereas the sign distance field actually is an implicit function, right? It's an implicit representation. So I just wanted to make you aware when you're looking this up in the context of reconstruction. So often these things are used for reconstruction. We'll talk about this later. I just wanted to make sure that you're not confused here. So, and since the literature is a little bit inconsistent, often what you will find for the same term is like neural fields, neural representations, or coordinate-based neural networks, and so on. It's a little bit inconsistent right now. I hope the research community will consolidate this, but I just wanted to make sure that these are not implicit if you get into this a couple of times. Okay, so these are the representations we've talked about. We have talked about images, 2D grids, we've talked about voxels, 3D grids, we've talked about meshes, piecewise linear approximations of a surface. We've talked about parametric surfaces like B-splines, Nurbs, subdivs, and we have talked about simple point clouds. And finally, we've talked about these implicit representations such as sign distance fields, which we will actually heavily use in this lecture to get good reconstructions. Now, we do know now what 3D is. And now one might ask, well, this is a lecture called 3D scanning and motion capture. So if you're doing 3D scanning, how do we actually obtain these 3D representations? What do we do? Well, traditionally speaking, if you're looking in computer graphics, people will tell you, well, if you want to have 3D content, like a game level or a character in a video game, you need to hire an artist, and that artist takes a bunch of tools and creates the respective content for you. And that content is a mesh typically, right? So like they start typically with a bunch of sketches, then they're creating a mesh. This is often a triangle mesh here or a parametric representation, like a subdiv surface or something like this. And then they're creating some textures and so on top of it, adding some lighting representations and so on. And then they can go ahead and visualize and render it respectively. But the traditional pipeline here is through various authoring tools. So authoring tools is the tools that artists are using in order to create the respective underlying 3D content. Mudbox, Maya, 3D Max, ZBrush, Houdini, Solid Edge, NX CATIA. These are kind of all various tools for kind of different application domains that are very, very powerful tools that artists are using or content creators are using in order to model the respective underlying 3D content. So this is typically, like traditionally speaking, how 3D content is being created, either in graphics or in civil engineering or so, when you model respective, when you want to model respective 3D geometries. Well, what you might already guess is that this is actually quite costly, right? So you have to, if you're looking, for instance, in your favorite movie or in your favorite video game, and you look at the credits, you're going to see there's going to be a lot of people who have actually contributed to the content. So there are a lot of artists and content creators that have modeled this stuff. So in a modern production, this is often the time limit, actually, right? So this costs you a lot of effort in order to create these kind of things by hand. And my motivation, for instance, as a researcher is I would like to automate these things to some degree, right? So I would like to go ahead and simply take my phone, right? Take my phone, take a couple of pictures, and I automatically get these kind of 3D representations from the real world. Hence, why we're ending up in the 3D scanning lecture here, right? This is essentially the idea that you can go ahead and create these things automatically. How this is being done, we'll talk about this in a bit. Okay, so this is more from an entertainment perspective, but we also have things like 3D scanning, what we just mentioned. This could be done in the medical domain, right? So for instance, have an MRI or a CT. Here you're going to have, this is an MRI here, right? So you have these magnets basically that they spin around. And through that, so by the way, by no means I'm a hardware expert knowing exactly how the MRIs work, but roughly you have a magnet spinning around, right? And what you're getting is you're getting essentially these voxel grids here, these layers of densities, like how the magnets are being turned. This could be done with other things too, right? It doesn't have to be magnet-based, but it could be also done on X-rays, which is essentially what CTs are doing. And the idea is basically you're getting these volumetric representations where every voxel, in a sense, has kind of a density value. And from there you can go ahead and extract slices of, in this case, the brain and the skull, I guess, but from the human body, for instance, and you can kind of look inside. And there's also then a reconstruction process going on where you can start extracting 3D structures from these MRI or CT scans and so on, right? And you can imagine these things are like super costly, right? This is not so straightforward. Like MRIs also take forever. Like if you have been and had a sports injury, you have to lie in these things for like 10-20 minutes, and this thing spins around you. And this is basically what they do, is they reconstruct this density field from where you can then further extract some sort of, or reconstruct some sort of 3D geometry, segmentations, and so on, and draw some conclusions what is wrong or not wrong with your body, right? And yeah, so this is kind of a very, in a sense, a very naive 3D representation what you're getting out there, because this is basically a voxel grid and density value per voxel. And yeah, and then you can have further downstream applications and so on. So we're not going to talk too much about medical imaging right now. There's specific other lectures for that. And there's, of course, a lot of knowledge and a lot of algorithmic design that has to go in there in order to get good reconstructions. But the core concept still applies, right? You're going to get a voxel grid. You sample basically with your hardware tools that you have at hand, with your scanners, and then you're going to get some respective values for these voxel grids. Okay. Now, what we're going to talk a little bit more is 3D scanning in the form of depth images. So, well, what is a depth image? Didn't we just say we want to have 3D representations and not images? Well, the idea is basically that you have a camera, and a camera sees a certain, from a certain viewpoint, it gets basically an image. But now, instead of just getting the image, in a depth image, you will also store the respective distance per pixel to the camera, right? So this is a depth image. You get color images, and now one of the tasks of the 3D scanning process is to take a lot of these depth images, put them all kind of together, and get a 3D representation as output. Okay, so this is something we want to talk a little bit in more detail. And we also want to talk into a little bit more detail what kind of scanners are potentially available in order to get there. So, well, I mentioned this kind of thing like a depth image. So the idea is basically have an eye point. This is where the camera location is. We have an image plane here. We have some sort of interesting object here in the scene. And now what the depth image is kind of storing is the distance from the eye point to the respective object, and it stores the distance on a per pixel basis, so you know exactly how far away the respective voxels are from from the respective camera, right? And yeah, so this is basically a depth image. One thing to consider is, one thing you could do here is you could kind of go ahead and say you having an eye point and you're measuring the distance, what is the length of this ray? That would be one option to store the z or the depth values. And the other option is to have a proper coordinate system with a y-axis and a z-axis that tells you how far away you are respectively here along the z-axis. Typically, we're going to do the latter one. This is like the z. When we're talking about depth images, typically talking about the z distance here in this coordinate frame rather than the actual ray length. So keep that in mind when we're talking about it. So I wanted to show you this quickly. So here, this is actually my phone. This is called, it's a Tango phone. It's like a very old prototype phone from Google. They actually have a depth sensor in here. So you see this, I think, flashing right now. This is like a light emitter. This is a time-of-flight camera. And what's happening is here, my phone right now captures basically a depth value on a per pixel basis. So you see something like this here, right? So if I hold this here, so now you see like these values here in the middle. You see kind of my, the depth values on a per point basis from me, which are being captured by the camera of the phone right now, right? And you could go ahead actually, and if I manage to do this, I could in principle scan myself. So now you see that, you know, it's scanning and reconstructing the environment to a certain degree. Okay, so it's a little bit difficult to do the demo here, but I guess you get the point that, you know, there's, for instance, phones right now, that have these depth sensors in it, and what they're doing is they're not just storing the RGB values on a per pixel basis, but they're measuring the distance from the pixel to the camera in various ways. We'll get into this in a second. And then you're getting these depth maps on a per image basis. By the way, the new iPhone has also a depth sensor in it. It has a Lidar scanner in it that also gives you a depth map if you're taking an image, assuming you turn the Lidar on. Okay. Often, in order to visualize the depth maps, what you do is you have this kind of HSV visualization. So the difference is basically you're mapping to HSV color space, and the U value is basically telling you it's just mapping the flow to a color range. So basically, if you have a red value here, that's further away. If you have a blue value, that is closer. There's various different ways of doing 3D representations here, visualizations here of the depth maps. This is one of them that I often use, but there's very different ones, right? The other one is just using grayscale. That was what we saw here. But yeah, there's different ones. This is just a visualization. But what you have to understand is on a per pixel basis, we're just storing the distance to the camera. Okay. Now, if we are talking a little bit further, there's a couple of terminologies we're going to talk about, and I wanted to mention them here already. The one thing I already mentioned, we have a camera here, right? We have a camera frame, it's X, Y, and Z. Z is typically the direction into the viewing direction. That's also why I'm always saying the Z values are stored. So Z values and depth values are kind of the same thing. And what we have is we have an image plane here, and then we have the intrinsic parameters of the camera that tell you essentially how to take the points in 3D and project them respectively to 2D. And you can always go back and forth with the intrinsic parameters between the 2D projections of the depth values and the respective underlying 3D points. So when you, for instance, having a depth image and you want to reconstruct a point cloud out of this one, or reproject the point cloud, that's basically taking every depth value at an XY location in the image and applying the inverse intrinsics, and you're getting back to the respective 3D points here. Okay. Yeah, we're having also the extrinsic parameters. That's also what you often will hear. This one basically goes from a world frame to a camera frame. So in this lecture, when we are talking about cameras or depth cameras, either one, we typically have intrinsic parameters and we have extrinsic parameters. So intrinsic parameters tell us how the projection goes from 2D to 3D inside the camera frame, and extrinsic tells us how do we go from the current camera frame to the world frame and vice versa. Right? So these are the two parameters that we need to keep in mind here. Okay. Right. So for instance, if we do this on a depth image and we have the depth values here on a per image basis, we back project these depth values to the current camera 3D points in camera space. Then you're getting results that look like these ones. So this is now the point cloud visualized. And now what you can do is you can basically apply a rotation matrix to it and view the depth images from the side, right? And this is kind of the idea of 3D scanning, right? You scan from one direction, get 3D values, but then you can virtually look at it from different perspectives. So you still see a lot of occlusions here, of course, but in principle, the idea is very clear, right? So we have one viewpoint that captures a bunch of depth values. You're getting these depth values, and then you project them back to 3D, and then you can look at them from different directions, right? And this is what's being done here, right? You see this person, you see where the shadow is basically, so you know this was from this side where it was being observed, from the right-hand side, and then you see, you see basically the respective points here rendered from a different viewpoint. This is actually a Kinect, the version 2, I think. And yeah, this is typically how you can look at the depth values then from different views once you back project them to 3D. Okay. Why a depth camera is useful? There's an interesting high-level debate that people have been saying a lot. And I mean, one of the larger pictures is we want to make computers see, right? We want to teach machines, in a sense, how to see like humans. And one of the motivations of depth cameras is very similar to what humans are doing, actually. And there's a specific reason why humans have two eyes. And we'll get to this now in the next few slides, because this is basically, the human visual system is essentially a depth camera, right? We have two eyes, and this is a stereo setup, right? So we have these two cameras, they're calibrated, our brain kind of knows where our eyes are, probably at least. And then based on that, our brain can reconstruct kind of like a depth map, and we can get depth perception as humans. So for instance, if you only had one eye and you close one eye for a longer period of time, you would have severe difficulties of playing tennis or something like this, because you can't estimate, you don't have a good depth perception anymore. Very similar idea, and algorithmically actually not so different. There's not a lot of intelligence that gets behind. This is not an AI thing. This is more like a classic computer vision setup where you essentially do stereo matching in your visual cortex, and that gives you essentially gives you kind of depth perception as a human. And yeah, so with that, the interesting thing is going to be, how can we possibly realize these depth cameras, and what are possible capture devices? And my idea here right now is I want to give you a very high-level overview first. I'm not going to go into all the depth of all capture devices. That would go a little bit beyond this lecture here. But I think what would be important is that you roughly understand how can you possibly reconstruct depth from sensor input, and what are the respective devices that make this possible. Right? Okay, so if we are talking about capture devices, there's basically two high-level distinctions we can make. We can say there's capture devices that are passive, and there's some of them are active. And the idea between passive and active is essentially that the passive ones, they don't emit anything into the scene. Active means they're emitting some form of light into the scene. Often this emission is in infrared channels, so humans can see it, but active means essentially you having some light being emitted into the scene, such that the measuring of whatever you're measuring later on would be easier. So if you're talking about passive, well, a passive capture device could be an RGB camera, straightforward, right? All you're doing is you have typically a CMOS sensor, right, that measures basically how many photons are being hit there on the pixels of this digital array, right? And that tells you for a webcam what the respective color of the respective pixel should be. That's passive, right? There's nothing, like my webcam right now doesn't emit any light. It's just receiving light, and the sensors tell me at every pixel what is the respective light color at each pixel, right? If you're doing stereo, same idea, except one camera. Now you have two RGB cameras. Again, human eyes, passive, right? We're not emitting any light as humans. This is a passive camera, and we have two of them, right? Could be a stereo setup, but it could be even more, right? It could be also a multi-view setup where you have tens, hundreds, and thousands of cameras, right? And this exists in various domains, and we also going to talk a little bit about these ones. Okay, so this is the passive ones. Then we have active cameras and active sensors. So for instance, time of flight is one of them. So time of flight, the high-level idea is kind of like you have a light emitter, and you kind of measure how long does it take that this light comes back and is being captured again. So it just measures basically exactly how it works. Is typically there's various different time of flight sensors. Could through the phase difference, but there's difference on a very high level. All you're doing is you're measuring basically how long does it take for the light from the emitter, hit a surface, come back, and that tells you how far the surface was away. This is active, and in this case you actually have to emit some light first. Costs you some energy on a phone. That's could be costly. For instance, what I just showed you, my phone here, this one here is a time of flight camera. So here light is being actually emitted and being sent to the scene. And then you can reconstruct the depth based on things like how long did the light take to come back to you, and that tells you essentially what the surface distance should be at the respective pixel location. There's things like structured light. Similar idea, you're emitting some structured pattern to the scene, you're capturing this pattern again. Based on how the pattern is being distorted by the scene, you can reconstruct how the respective surface looks like and how far it is away. Laser scanners, Lidar, same idea. In this case, Lidar and structured light in a sense are very similar, except the light emission is a little bit different in the way the scanning works, but very similar thing, right? You shoot a laser in a scene, you check where the laser is, and based on that you can reconstruct, can triangulate where the surface should be, and that's also active, right? So it's clearly an active sensor. What I haven't mentioned here, you can even think about like radar or so, right? Radar are also sensors, right? Can actually be used to reconstruct depth values too. They reconstruct a little bit more, but they also active sensors, right? So you have the outgoing radar pulses, and then you can basically reconstruct certain things about the scene, such as depth or velocity and so on, also active. Okay, now what I want to talk a little bit about more is about the depth cameras, right? How can we perceive depth with a computer, with a machine, and how do we build these cameras together? And I want to specifically mention one device that I really like a lot, and this actually got me into this research area. So when I started my my research in this field, the Microsoft Kinect came out, and this was kind of a really cool thing, because suddenly these traditionally super expensive depth sensors you could buy for basically $100, right? So pretty cheap consumer devices now that could actually capture relatively high quality depth. And in research environments, even today, the Kinect is still one of the go-to devices that a lot of research projects are using when they're playing around with their research methods and algorithms, if they want to have relatively easy to acquire depth. Okay, so the Kinect version 1 is a version where we have essentially a structured light sensor. So we have three. You see, when you look at the Kinect, you have three sensors here. One of them is an RGB sensor. One of them is a light emitter that emits a structured pattern. And the third one is going to be a camera that captures the structure pattern. And this one of the cameras is basically an RGB camera, and the other one is a camera that works in the infrared domain, because these patterns are typically emitted in the infrared domain. And this is structured light. This is what the Kinect version 1 does. There's also the Kinect version 2. Kinect version 2 is a time-of-flight camera. So from a technology standpoint, these two cameras have nothing in common. They're completely different. Interestingly enough, the Kinect V1 is still better for most research purposes, because the Kinect V2 has a lot of like lens distortion and so on. So some stuff is not so easy there. So a lot of the times when you deal with like research methods, research papers, Kinect V1 is the way to go. And then there's stereo cameras. This is basically, you have two RGB cameras here. They are mounted on a rig, or in this case on a board, and they're calibrated. So you know, typically in stereo cameras and stereo setups, you know the calibration between those, you know the extrinsic parameters between those two cameras, right? Remember extrinsic parameters, like how do the two cameras relate to each other, how do they relate to a global coordinate frame. We have active stereo, similar idea. You have like a stereo pair here, but here on top you have a projector. The difference now is basically that stereo cameras, for instance, they're having a really tough time when you're dealing with textureless surfaces. If you have a white wall and you have a texture camera, you're not going to get good depth values. We'll talk about this, why you don't get good depth values, because you can't basically do the stereo matching. But if you have an active stereo sensor, this still works, because there's a pattern that's being projected, and that fixes kind of these textureless regions. It's kind of funny. This projector here is actually the same as in the Kinect here. This is like we did this in a research project, we pulled this one out and put it on top of this one. But there's a key difference how the methods here work. So in structured light, the pattern that you're projecting into the scene, you need to know. You need to know exactly how this pattern looks like, you need to calibrate it, and based on the distortion of the pattern, you can reconstruct the depth values. In active stereo, that's different. Typically, you don't care what the pattern is. You just care that there is a pattern such that you can do better stereo matching afterwards. Okay, we have Lidar, light detection and ranging. That's the long name for it. It's a laser scanner, right? So you have here on top of this spinning thing, right? This basically shoots a laser around, and based on every ray you're shooting out here, you can reconstruct the respective depth values at this point. Lidars are typically or very frequently being used in outdoor scenes, like self-driving cars. They mostly use Lidar scans. The reason is very simple, because they have a relatively large range. each measurement is relatively accurate, and they aren't super sensitive to like lighting changes. Like stereo, so or time of flight could be a little bit problematic often when you have stereo, when you have outdoors. So some of these, so for instance, the Kinect channel thing, Kinect V1, Kinect V2, they don't work outdoors. Very simple thing. They're using an infrared pattern, and if you going out at a day like this today, your infrared camera, they will see basically a fully saturated image because the sunlight is pretty much all infrared, and that's going to oversaturate everything. So these Kinects also, they don't work outdoors. Lidars, great outdoors. They're not as dense, but they have a larger range, and because of that, they're mostly used in like self-driving car scenarios. But there's also laser scanners, of course, for indoors. This is an example. This was the Cyberware laser scanner. So here, like, person sits on a chair, and that laser scanner basically goes from the top to the bottom and creates a very high quality 3D model of a scene. Okay, so now let's go into a bit more depth of each of them, right? That's why they're depth cameras. So here you have a bit of an overview of what these cameras are, what they can do. And I think this is pretty important actually. When you ever do something in like 3D computer vision or generally computer vision, right, you have to understand what cameras are available and what is the right thing for your current setup. Okay, let's talk about stereo cameras. So if you had to build your own stereo camera, it's actually pretty straightforward. So what you do is you take two RGB cameras, you synchronize the video capture, so you make sure that they take the images at the same time, and then you calibrate the two cameras, and then you do stereo matching. We're not going to go into all the details of stereo matching, but I still wanted to give you a very high-level overview of how it works. But there's actually, right by now, there's a lot of literature how good stereo matching works in practice. Okay, if we are talking about cameras, generally speaking, the one thing I already mentioned is we're going to have extrinsics and intrinsics. So intrinsic is on a per camera basis, essentially the projection. So each of these two cameras will probably have their own intrinsic matrix. Even if they are very similar, these intrinsics, they're going to be specific to the current camera because, you know, the production process is not perfectly identical. So each camera looks slightly different on a hardware level. So the intrinsics, they have a bunch of parameters. We'll go into these ones. What's important right now is we have the focal length, fx and fy. We have a principal point, mx and my. There's also this q parameter here. Often this one is just set to 0. Depends on the camera model you're using. But basically you have these intrinsic parameters here that tell you the calibration on a per camera basis. And then you have an extrinsic calibration that tells you how to go from this camera's frame to that camera frame, which is typically rotation and translation matrix. Okay, if you build your own stereo camera, the one thing you have to do quite a bit is you have to calibrate the two cameras. And there's a lot of tools to do that. So here's one tool. This is basically Opencv, I think. So you typically take these checkerboard patterns. And I'm not going to go in all the detail how the calibration process works, but checkerboard patterns are typically good at detecting corners, right? Because you have white and black tiles. And based on that, you can establish correspondences, and calibration means nothing else but figuring out the intrinsic, the extrinsic parameters of your cameras. These are typically nonlinear optimization problems, taking a bunch of these images here as inputs, taking the corner points of the checkerboards, and then finding and optimizing for the respective parameters here. Okay, so let's say we've done that. We spent a bit of literature looking up how intrinsic, extrinsic work. We know how the optimization here works to calibrate it properly. So now for our stereo pair for these two cameras, we know the projection matrices basically for each camera, and we know the respective extrinsic transformation between the two. Once we're there, we can start doing this process, what we call stereo matching. And stereo matching is kind of like this. So what you do is you have an object here. We have two cameras. We have their respective image planes, right? And these two, they capture now an image at the same time slot. And now what we would like to know is, we would like to know if we have a point here and we have a point here, whether these are the same surface points, right? And now what we have to figure out, we have to figure out a way, if I know that this point and that point is the same, I can go ahead and I can triangulate the respective depth points in each of these cameras. But when people talk about stereo matching, what they mostly mean is they wanna figure out this point and that point is the same point. They want to figure out this point here maybe, and that point was the same surface point. And we'll talk about this in a little bit. How do we find that out? This is basically a feature matching process. And out of this feature matching process, you know correspondences between the two cameras. And based on these correspondences, you can do some triangulation. And you can figure out where's the respective 3D point, or what is the respective distance here to the camera. This is how stereo cameras work. Okay. So how does it look in practice, right? We have the left and the right camera's image. There's a few things you should know. There's this epipolar line. This whole thing is called epipolar geometry. And then there's the epipolar line that says, okay, if we're having like this image and this image here, we can put a line here through. And now what we would like to know is we want to figure out where these correspondences are. That's what I just mentioned. And then we want to take this epipolar geometry into account and triangulate where the respective 3D points are. One thing that is typically really difficult is finding the correspondences. So knowing that this point here in this image and that point here in that image were the same 3D point. And this is a feature matching process that is really, really tricky. And there have been thousands of research papers around it. How do we find good feature points between these two cameras? So it's a really, really hard problem. Once we have the feature points, we have a disparity between those two. And based on this disparity value, we can relatively easily calculate the distance here. So there's typically a step here that makes this problem a little bit easier. So instead of just matching arbitrary points here, what we would like to have is we want to have this nice epipolar line here that is basically a straight, if I put these two images side by side, I want to have a parallel line between all feature matches, right? And this is a process called rectification of the images. So what you do here is you essentially taking two images, and now let's say we have a bunch of correspondences between these two images, like this point here and this point here we matched, this point here and this point here we matched. And now we take the epipolar lines here, you see, okay, there's like, they are not on a straight line, right? Which is obvious because these cameras were not just, they were looking from the side, right? And what you want to do is you want to basically find a common backplane where you back projecting virtually these two images such that they are on one plane. And this process is called rectification. So basically what you do here is right now, right, you take, this is the original setup, you have a camera here, you have a camera, an image plane here of the other camera, and now what you want to do is you want to back project these ones such that these lines here become all straight. And this is the process of rectification. So we're projecting each image onto the same plane, which is parallel to the epipole, right? And then we resample the lines to place lines in correspondence and minimize the distortion and stuff like this. Okay, but high level concept, you just want to project the two images from both cameras onto the same plane. This is the rectification process. And in practice, this looks like this. There's many papers that do this. This is one of the Loop and Zhang papers. That's one of the papers people use. And the idea here is basically at the end of the day, this rectification looks something like this, right? So now these lines here, they are all going to be parallel to each other. And now the matching of the stereo matching process is going to be a lot easier once you have done this rectification, right? And by the way, rectification, what you need to do is you basically need to know the intrinsic, extrinsic calibration of the camera, then you know where the image planes are, and then you back project the pixels to a common plane further back, and then you have rectified it, right? And now what we have to do for the stereo matching process, we're doing this typically on these rectified images, and that is a lot easier actually than doing it on the original images, because now all we have to do is we basically have to take a point here, right? And we just slide a window through it and check, is there any window that looks kind of the same what you have seen on the left-hand side, right? But because these cameras haven't seen exactly the same thing, they are from slightly different viewpoints, you will see that this is actually not exactly the same, right? So there's going to be some small difference in in locally how these points look like. And some points you might not even see in the other image because they might be occluded. But the high-level idea of like the stereo matching, we have the search window. So for each pixel, we just check along the epipolar line to find the best match. Right? And this is literally what you're doing here. You just go across the line, you have this kernel, and you're checking out where do we find the best match. Okay, and I already mentioned this is a complicated process because there's no exact match. So what we have to do is we have to use some sort of feature descriptor to determine what the best match is here, right? So for instance, in this case, we determine this is the one on the left-hand camera, and this is the one on the right-hand camera, and these two are actually matching. So this one looks pretty good. But how do we know whether it looks pretty good? Like, how does the computer know whether it looks good? Well, the simplest thing is you just take basically an L2 distance. So you take this sum of square distances, this n SSD, right? You just say, well, for every pixel here, you compare it with every pixel here. So every pixel here on the left with every pixel here on the right. You just sum up the error here, and you're just gonna go ahead and check out where this value is the lowest, and this is probably your match then, right? This is a naive thing to do. In practice, that's not state of the art anymore. You can do a lot more complicated things. You can do a lot more complicated feature matches. But let's just pretend this is the easiest thing we're gonna do, right? So we can do stereo matching basically for every point on the left-hand image. We find the respective best point on the right-hand image. We do this for every pixel on the left-hand side. So this is quite costly, right? This is computationally quite something to do. We find the best matches respectively. You can do some greedy version, right? You pick the first one that you find, and then the other ones can't find it anymore, and vice versa. There's also a bunch of strategies there, but conceptually it's pretty straightforward, right? You just do this kind of brute force search along the epipolar lines. Where do we find good matches? Okay, now there's a concept of sparse versus dense stereo matching. So dense matching is what I just described essentially. Dense matching is take every point, take every pixel on the left-hand image, and go along the epipolar line and force that you find a match on the right-hand side, right? So you have to find that. And you're doing this for everything with a relatively, let's call it weak descriptor. Like this SSD here, the sum of square distance, is like the weakest descriptor you can imagine, right? It's not very smart. It doesn't account for lighting or reflection changes. It's not a good descriptor in principle, but this is like the most naive descriptor you can do, and often this works for dense stereo matching. But now there's also a thing called sparse stereo matching. And the high-level idea is, well, sometimes this SSD metric is wrong. For instance, if you have a white wall and you have two white walls, then how on earth should you figure out where to go? Because everything kind of matches perfectly. Everything is a white wall. There's no discriminative color patterns that tell you where to do the stereo match. And because of that, you could say, well, we don't want to find a match everywhere. We just want to find a match in important locations where we know we have good matches. And this is the concept of sparse stereo matching, right? And one way to do sparse stereo matching is say, well, instead of using this SSD descriptors, you can go ahead and say we're using actual feature descriptors that are much more sophisticated. So for instance, we can use sparse feature descriptors such as SIF, SURF, ORB. These are handcrafted feature descriptors that people have studied for decades, basically. Like SIF is a very powerful descriptor that gives you a discriminative point, and it tries to identify, tries to figure out, is the other point in a different image, for instance, do they belong to the same 3D point, basically. Okay, so this is an example how this looks. So this is basically, this is a stereo pair. There's two images, and now there's a bunch of SIFT key points that were detected, and these are the SIFT matches that you found in the stereo pair, and the respective red lines tell you which ones matches with the respective other image, right? So you know, again, this point here matches with that point here, this point here matches with that point here, and so on, right? So typically now, the better the image quality, often the higher resolution, the easier or the better these matches are going to be, right? And this is sparse stereo matching. So basically you're saying, well, we're not going to get a depth value for every point. We're just going to get depth values for these sparse points. But we can guarantee a certain level of accuracy So the quality of each match will be a lot better than using a dense matcher. Can do both. Can do also combinations of these two. There's many different versions of it. I just wanted to highlight the two extreme, right? One is dense matching. For every point you're trying to find a match. One is sparse matching. You're only doing for discriminative feature points. Okay. Yeah, this is basically stereo matching. Now I'm going to talk about a few implications. So in this search window, big question is how big should the search window be? Like when we do this sum of square distances in the dense matching, there's two options. We can have a smaller search window and we can have a larger search window. And the idea is if we are having a small window on the left-hand side, window size of 3 versus a window size of 20. And this is typically what you get in terms of the resulting outputs. So if you're having a smaller neighborhood, you're going to get a lot more detail, potentially, right? Because you're not over-smoothing the matches, but you're also getting a lot more noise. So smaller neighborhood means more detail, more noise. Larger neighborhood means more over-smoothing, less noise, but fewer details, right? So this is kind of a compromise of the search window. So it's not easy actually to determine this window size, because this really depends on the setup that you have, on the stereo baseline. It depends on the window size basically depends on the images and so on, right? And how many features you have. Now, what I mentioned before was we can do this stereo matching in a greedy way, right? So we can go ahead and we take the first pixel on the left-hand image. We're trying to find the match on the right-hand side. And once we found this match, we can never match the right-hand pixel that we just found to any other pixel. So there's right, you can't have, it's not possible to do that. And it turns out this greedy thing, what I just described, is of course not that ideal, right? Because in theory, what you would like to do is you would like to have globally the best optimal matching that gets you the optimal energy in a global sense, where you find the best matches such that the overall SSD energies are the smallest compared to only a single match. Yeah, and this is of course a very challenging problem, because now you have suddenly an NP-complete assignment issue. Like which feature should you match, which pixel on the left-hand image should you match with which pixel on the right-hand image, right? This is actually an NP-complete problem. It's really difficult to do that. And the search time correlates with the window size, right? Like larger window size makes everything much more complicated. And there's been a lot of methods that have been trying to do this. One very popular one is to approximate this problem with patch match stereo. So patch match is basically a method to first randomly assign some of them and then iteratively improve the assignment and then getting better and better matches. There's this famous patch match paper by Barnes et al. This was a SIGGRAPH paper, I think like 2010 or so. And then Lidar et al. They used it for stereo matching in a very effective way. And this is probably what still a lot of stereo matches use today. It's a very good compromise between runtime and quality, basically. And you can actually do this even in real time. So a lot of cameras even implement this in hardware to some degree. So you can get real-time feeds of stereo cameras, right? So the way you do the matching is kind of important here. So this greedy matching, what I said before, is not so ideal. So you typically want to do some sort of iterative approach to find better matches. Okay. Yeah, I want to show a few failures where stereo matching is not that ideal. And the main thing when stereo matches fails is basically correspondence search. So if you, for instance, you have specular surfaces, right? So this is a good example here. Here you have a very specular surface, right? For instance, this part here from this view looks just very different than here. Why? Because it just changes, the appearance is changed based on the viewing angle. So one camera sees it differently than the other camera, which unfortunately, by the way, a lot of surfaces in real life are non-Lagrangian. So these specularities, they kind of kill the stereo matching. Difficult problem. Ideally, you would like to have feature descriptors that are robust against that. But again, difficult problem, not easy to do. Most of the time, you're just going to get wrong matches here, going to get outliers. It's not ideal. Another thing that's really difficult is occlusions. Occlusion, when you have like fences and so on, very difficult. Like look at this fence here. Good luck doing stereo matching between these two images. super difficult, right? So some camera just sees some stuff that the other camera doesn't see. So if you have a lot of thin structures like these fences or iron bars, they're relatively hard to reconstruct with stereo because you just don't have them in both images at the same time. You have a lot of occlusions. Same thing, what's also a problem is repetition is an issue. If you have the same thing over and over again, then a feature descriptor might tell you this is a perfect match because that looks kind of identical, but it was the wrong instance of the same repetitive pattern. So yeah, occlusions, repetition, really problematic for stereo matches. Typically gives you bad stereo values, very hard to deal with. Again, for repetition, you can do something. You can try to basically make search windows larger and try to find more globally optimal solutions, but still very, very tricky, very difficult actually, right? And yeah, and then the obvious problem, what I mentioned already a couple of times, textureless surface, super difficult to reconstruct, of course, because now everything looks the same in your feature distance, and everything kind of matches the same. So if you want to do a reconstruction of a white wall with a passive stereo, no way, can't do that. Don't get anything out of this one, right? Yeah, I wanted to also talk a little bit about what I mean, what I'm saying here is, right, the correspondence search is kind of the key of good stereo matching. This is the hardest part in the correspondence assignment. That's kind of what this patch match is doing. But the correspondence search or the correspondence matching is the hardest part of the stereo matcher. And this is not so straightforward. So traditionally, people have been using SIFT, SURF, these handcrafted descriptors. But obviously, neural networks are very good for this task too. And this is where a lot of stuff comes into play. So I wanted to quickly explain that how a neural network would do that. So a CNN, a convolutional neural network, is actually a perfect feature matcher, right? So what you can do is here, you have a point here as input, take the neighborhood, feed this point here into some input. You have this point here, you also feed this one into some input. And what you get there is you just have a feature distance, you have some ground truth. How to get the ground truth is a different question, but let's say you have some ground truth. You just train this network on good matches versus bad matches. You have the Siamese architecture here where you share the weights between these two CNN towers. And the high-level idea is you basically learn what good stereo matches are and what bad stereo matches are, right? I'm oversimplifying this. In state-of-the-art papers, there's a lot more to it. There's things like cost volumes and so on. I'm not going to go into all the details here, but the high-level idea is very simple, right? You basically want to make sure that you have a local neighborhood around a point here, you have a local neighborhood around a point here, and you're basically learning a feature descriptor and tells you how similar should we consider these points to be if we want to do good stereo matching, right? And there's a lot of papers that address this kind of problem, and it's still very exciting how to do it right. And it turns out, of course, these things work remarkably well if you train them well enough, if you have the right training data and so on. So stereo matching with deep learning, very cool topic. A lot of papers already came out on this one, and they also show pretty remarkable performance. So state-of-the-art stereo matching uses some combination of this with traditional epipolar geometry reconstruction, right? Yeah, this was a Siamese network. So for those who don't know it, the idea of a Siamese network is you have basically two towers of a CNN, or it doesn't have to be a CNN, but in this case it's CNN, and the weights are shared during training. So this encoding of this and this is the same encoder basically that gives you the features for the respective patches. And here you have, for instance, an L2 distance that tells you how close the descriptors here should be. So yeah, super exciting if you're interested in Google stereo matching for deep learning. Cool projects can be done around this one. Okay, yeah, if we're talking now about matches, I actually didn't go all the way through how to actually compute the depth now. We just said, oh, all we need is matches and that's it. But we still have to do this triangulation, what I meant, right? So what we have here is we basically have our stereo setup. We have a left camera, we have a right camera. This is rectified. We have an epipolar line here. And what we do now is basically we compute the z value. This is the depth value that we want to compute. And this value is based on three things. It's based on f, the focal length. This one we know from our intrinsic calibration. It's based on the baseline. That's the the baseline is the distance between those two cameras. That one we know from our the baseline we know from our extrinsic calibration, and d, that's the disparity. The disparity is the distance between this point and that point on the epipolar line after the rectification. So d is basically, so f and t, these are given by the calibration, and d is what we're getting through the stereo matching. And then in order to get the depth value, we just have to do this triangulation, and then we get the depth values respectively. Yeah. There's an interesting thing which I haven't really talked too much about. So one big question is, what should be the distance between these two cameras? Like, what's the baseline between those two cameras, the stereo baseline? Yeah, that's a very interesting question, because this has a lot of implications. So if you have a wide baseline, it's going to get a lot easier to find, if you have a wider baseline, it's a lot harder to find the matches, right? Because you have more distortions and you have more occlusions. You might have more specular effects and stuff like this too, right? So the further the viewpoints of the camera is apart, the harder the matches are going to be found. But if we find it, then the triangulation here basically becomes a lot more well-defined, right? So the wider the baseline, the easier the triangulation becomes, and the more accurate the depth values will be. If you have a small baseline, a small disparity error basically results in a large distance error, right? It's just the conditioning of the problem, right? If you have this triangulation as a skinny triangle, that's a problem, right? If it's too small. And in practice, you have to definitely go ahead at some point and say, well, disparities are not just pixels anymore, but they're actually subpixels. So, right, when we're doing stereo matching, these values here, if you're going quickly back, oops, let me go back here. Right, so this one here, the difference here, this is typically not on a per pixel basis, but on a subpixel basis. Yeah, this is very important actually if you have small baselines. Otherwise, it just doesn't work, because your triangles are so skinny, and like being 1 or 2 pixels off makes a massive difference in the depth. And then you get these staircasing artifacts in stereo matchers that result in staircasing in the depth values, which is not so ideal, right? Okay. Yeah, this is in a very short summary was stereo matching. And now we're going to talk a little bit about extension of this, but the core concepts of how to compute disparity values, how to do calibration, how to compute the final depth values at the end of the day is always going to be very similar. So there's things like multi-view stereo. That's basically just an extension of what we just had, except that we have a lot of cameras and we have different pairs where we can do stereo matches in between. There's also methods that actually can do matches between like triplets of cameras and so on. But for the most part, people actually don't do that. For the most part, people just try to take all combinations of pairs between those camera arrays, and then they're going to try to find the respective disparity values. So here are two camera arrays that I found pretty cool. This is the Stanford multi-camera array. I think they had 64 cameras, right? So there are a lot of different combinations of stereo pairs you can compute. They were used for, this is basically light field camera. Like one of the ultimate result was the Litro cameras that came out of this, if you're interested in that. But this is just multi-view stereo, right? So you're having n of these cameras, and then you can do stereo matching between multiple of them, and that gives you a better result at the end of the day. Okay, this is the Cmu Multi-Camera Setup. I think this was done by Takeo Kanade already a long time ago. But these camera setups, they are like 360 setups in a sense, right? So here, or not 360, it's like a dome on top of it with the upper hemisphere. And then you have these cameras distributed around, and the goal is you want to reconstruct good 3D, you want to get good 3D reconstructions here around there. Yeah, so I think this is pretty good. You can do the same thing what I've just explained, right? You just do stereo matching between pairs, and then you can get depth values. But there's of course other tricks then to combine the information from multiple cameras better. Okay, but yeah, all of these things right now, what we have talked about is all passive stereo, let it be multi-view or just do cameras. Now, let's go ahead and talk about active stereo. So active stereo is in principle the very same idea that what we have just seen. The only small little difference is we have a projection pattern here, right? So we have a projector that emits some pattern, and the whole point of an active stereo camera is basically to make sure the correspondence matching becomes easier. Why is it becoming easier? Well, now we have a pattern, and this pattern can be recognized much easier than a white wall, right? So if you have an active stereo camera, I'm going to get depth values from a white wall, that works perfectly because now you have these patterns that you're projecting, and they can be matched, and because of that you get depth values. Very similar idea than the passive ones. The methodology in terms of the matching and everything is pretty much all the same. The only difference is you have an IR pattern. What's important to know is that this IR pattern, this infrared pattern, it's not always IR, it's not always infrared. It could be also a pattern in visible lights, but for the most part you want to use IR because you still want to capture the RGB images and you don't want to have some weird pattern in your RGB data. Okay, and now what you want to do is same thing as before. You have the stereo matching, you're going to get depth values and so on. So I want to show you one example of an active stereo camera. This is a Intel RealSense. Don't be confused. There's a lot of different Intel RealSense depth cameras. This is the R200. This is one of the first ones. I just picked this one here because this is a kind of an interesting design. So what they have is this is an IR laser projector. This is the active pattern. This is a color camera here. And then they have two IR sensors. They have one IR sensor here, and they have one IR sensor here. This is the stereo pair, these IR sensors. And this is the pattern that is emitted. And this is an active stereo camera, right? By the way, the color sensor here doesn't do anything with the depth. Like the depth is just based on these two IR sensors. And what's interesting is now there's basically two modes of this camera. One of them is an active mode, and one of them is a passive mode. So active mode means we are emitting stuff into the scene. The projector here is active. But again, you can see it's an IR pattern. And then there's a passive mode where you don't have it active. And like this gives you a bit of a sense of where these things are being used. If you want to do things indoors, you most of the time want to be in active mode because that's more close range. You want to have more features on the surface to get a more detailed reconstruction. Whereas if you're outdoors, as I mentioned before, you have sunlight, the IR stuff from the projector is going to be completely overshadowed, right? So you don't see that. So the exposure of the IR sensors has to be tuned down. Otherwise, you're going to be overexposed. The IR pattern wouldn't be even visible here. So basically, this is just passive stereo in IR space. You need some sunlight here, or some daylight basically, to get some IR light in it. And this is just passive stereo matching in outdoors. What's kind of cool is the sensor kind of switches dynamically in between, right? So it does sometimes, like indoors, it's close range, then it's active mode, and outdoors it's going to be passive mode. So this one can do both actually. Yeah, this is a very cool design actually. Maybe the quality could have been a bit improved at this one, but the Intel had a couple of iterations to gain basically new sensor types on top of it. Okay, this is one of the sensors that we built. We, like the team at Microsoft Research built. I was an intern there at this point, so maybe I didn't build it personally, but this was done by Christoph Rehmann actually. He has done a fantastic job at building this hardware setup. And the idea here is you have two cameras. These are single lens cameras, and you have an IR pattern projector. Similar as before, but this one is always in active mode, so to say, if you're comparing to the Intel one. And these cameras, these cameras are kind of interesting in a certain way. These cameras, they have a beam splitter. I'll explain to this what it is, but basically, this is a camera that can capture RGB and infrared at the same time, but it gives you separate images, one for the RGB and one for the infrared, right? So on the infrared side, you want to do the stereo matching based on the IR pattern, and on the RGB, you just want to have pretty RGB images. And then you can do patch match stereo, and you can get actually very high quality reconstructions, for instance, for a face. Yeah, if you're looking at the beam splitters, it's kind of interesting. This is maybe not the main focus on the course, but I find it pretty cool. And so the way this works is basically you're having here input light, right? You're having two sensors at the end of the day. They both capture at 30 hertz. And basically what you have is you have the beam splitter splits the infrared part and the RGB part apart. So all the RGB part gets on this CCD, and all the infrared part gets on this CCD, right? So now you have two separate streams of images, but they are identically captured at the same time period, which is typically not so straightforward to do. So I think, yeah, that is That is kind of cool. And yeah, this is how you can do now stereo matching in infrared while having an active sensor and getting very relatively high quality data out of it. Okay, all right, let's move on from stereo now. Let's move to structured light. So structured light is, from a conceptual standpoint, actually not so different. Except of two cameras. The difference is now we have one camera and we have one projector. So here we have a stripe projector, for instance. Well, we have, it could be a stripe projector, it could be laser pattern or whatever, but basically you have one projector and you have one camera. And the idea is you project some pattern in here, and then you figure out with the camera what is respectively observed. So this could be with a stripe pattern or with a single line of a laser scanner or something like this, right? But similar idea, both of them are structured light in principle. And the core concept right now is that you have here the camera, you have here the emitter, and the core idea here is that now we're emitting a bunch of different, let's say, color values. Let's say we have 4 color values here: red, green, yellow, and pink. And the idea is basically now in the camera, well, we just find, oh, where in this image did we find the red value? Where in this image did we find the green value? Where in this image did we find the yellow value? And where did we find the pink value? This is a bit oversimplified with these colors right now, but this is the high-level idea, right? So you want to emit a known pattern, in this case the color values, and in the camera you want to figure out where were these values, and based on that you're going to get essentially stereo matches between the projector and the camera, and then you can triangulate again, and you know where the respective depth value should be. The important thing here is that this pattern has to be known, right? So this can only work if the camera kind of knows what the projector is emitting, right? Otherwise, no chance, don't know what to do. By the way, the simplest and dumbest pattern is a single point. It's a single laser point. Single laser point, I just find where the laser point is. That gives me a pretty good match because I just have to find for the laser point. Downside is I only get a single depth value, right? I only have 1 pixel basically. So in practice, in order to not just have 1 pixel, you're going to have much more complicated emitted patterns here, that based on these pattern distortions, you can figure out where the respective matches were in this pre-calibrated pattern, and based on that you can kind of do the stereo algorithm. Okay, this is what the Kinect V1 is doing. Kinect V1 has an IR emitter, known calibrated camera pattern. It has a color sensor that's not being used right now, but then it has this IR depth sensor that can record the IR emitter pattern and then can reconstruct the stuff based on this known pattern, right? This is what the Kinect V1 is doing. Hardware-wise, this looks like this. And all this is a microphone array, a tilt motor, stuff like this, but not so important right now for the exercise of this class. For us, what's important is the IR depth sensor and the IR emitter. Again, everything in infrared. You don't want to see a pattern in front of your room when you want to play games on an Xbox. You just want to make sure that you can split the RGB and the IR here. Okay, how does it look in practice? Well, in practice, we have the Kinect. This is this calibrated pattern. This looks like this in IR space. If you look at it, it's kind of funny. This is the RGB input, looks like that. And then you just do the stereo matching, what I just mentioned, between this pattern and the camera, and then you're going to get depth values that look like these ones. So Kinect, pretty fancy sensor. Very cheap to make too, because you only need basically 1 emitter and 1 sensor. So not a lot of hardware requirements, and that's done with this calibrated pattern. Gets pretty good depth maps, and it actually can do it at 30 frames a second, which is kind of cool. So 2011 or whatever, when it came out, this was the sensor to go to. It was actually, I'm not sure if it still is, but it was definitely the most quickly selling consumer electronic device ever at the time. So I think quite remarkable engineering what they put in there. So I was very excited. So for me, that really got me into the area, and we did a lot of cool stuff around it. Okay. Yeah, that's structured light. Structured light, algorithmically very similar to stereo, except you need to figure out the way to deal with this calibrated pattern and how to do the correspondence matching afterwards. By the way, what I mentioned, Kinect outdoors doesn't work. This pattern is going to be completely overshadowed by sunlight. So yeah, can do outdoors, can only do indoors. Okay, let's go to laser scanning. Laser scanning it's kind of like structured light, right? It's not so different. So you could imagine laser scanning to be a single laser pointer in a projector. That's your known pattern, so to say. You can find the pattern in the camera, and based on the calibration of your camera, you know exactly what the distance is. High-level idea, very straightforward. This is an example of a laser scanner. Here you already see that this is not just one point, but instead it's a stripe, right? It's basically going in scan line order. And then this thing is going through the entire object of interest. Here, this was a very cool project by Mark Levoy and his group, the Digital Michelangelo project. So here the idea is basically you have this massive laser scanner and this like massive Michelangelo statue, but this thing is really tall. That's like bigger than an actual human. So pretty big statue here. It goes up. It basically goes down all the way. It takes forever because it has to go scan line by scan line through it to get a high resolution. And then you're going to get reconstructions that look like these ones. Right. Yeah, so I already mentioned, simple version, just take a laser pointer, straightforward. You have this point here, you find the point in the camera. If you're calibrated, you can basically do, again, stereo triangulation and can figure out the distance here. Common thing is what I mentioned is you do it scan line by scan line. This is scan line. You see the scan line. It's a very small scan line. Smaller scan line, longer it takes because you have to make sure you cover everything in your surface. So it's a slow process. So compared to a Kinect or so that does like Kinect does 30 frames a second, this thing to scan this whole statue, I don't know exactly how long it takes. Best case minutes, probably hours, right? Depends on which laser scanner and so on. But it's also the speed here is also a trade-off between quality and speed, basically, right? It's a bit of a trade-off. Okay, laser scanners, they have one big advantage is they are like really accurate, right? You're gonna get reconstructions of a room here, looks like these ones. Yeah, looks pretty accurate, right? Can't say anything about it. Depending on the density on the laser scanner, the density changes, of course, but laser scanning is super accurate, but takes a long time. So doing anything in real time in a very dense scanning fashion with a laser scanner is not so straightforward, right? That's very difficult. But yeah, laser scanning is cool. It's super expensive. Laser scanner costs a lot of money. Whereas Kinect is so super cheap, but the quality, of course, of the depth value is a lot higher. Okay, then we have Lidar. Yeah, Lidar is light imaging detection and ranging. Similar idea, right? You have a laser beam, basically, you're figuring out how far away you are. The idea here is, so Velodyne is one of the manufacturers that makes these little well, pods or whatever you want to call them that are sitting on top of the cars. Looks like this, right? This is the laser. This is the lidar scanner here. And the idea is this thing spins, and you actually don't get a single 360 image at the same time. So it does it through temporal multiplexing, kind of. Does it get the surrounding environment? And then you have to do a bit of registration because the car is, of course, driving, how to align these things. But there's a mechanical spinning thing on top of it that basically gets you the respective outputs here. Okay, yeah, this is from a lot of autonomous cars that use this. Google Street View used it in the Street View cars. I'm not going to go into too much detail here. From a methodology, it's very similar to standard laser scannings, basically, right? And you see actually in modern cars, this is a version of Uber's car, you see there's a bunch of sensors. There's the LiDAR scanner, typically 1.4 million points here per second, so it's quite an impressive scanning speed here. You have a bunch of cameras looking forward. They do separate stereo matching typically. They have GPS antennas in there. They have LiDAR modules on the front, and so on. So modern cars, they have a crap ton, modern self-driving cars, they have a crap ton of these sensors in it. This is the famous Google car, I guess, right? This one has only one of them. But the new cars, they just are packed with LiDAR scanners, stereo sensors, and so on, right? Again, we're not going to go into all the details how the LiDARs work in all the detail. Not so important, but what's important is basically that you understand how stereo matching works, right? You understand the concept of active sensors when you have like structured light and so on, and so Okay, so laser scanning the environment, yeah, looks like this. This is typically what you see from a Lidar scan in a car, like very sparse, but each point is very accurate. Okay, so what can you do with it? Actually, you can use for 3D printing here. And yeah, this is like, I want to show this quick video because I found this pretty cool. So what they do is they kind of combine a laser scanner with a MakerBot. So the idea is here they have, if you look at this, they have the laser scanner on the top. You put the object of interest on this platform, it's going to spin around and scan this object in. And then afterwards you can put this into a 3D printer, and that gives you then a printed output. And they try to streamline this, right? And I found this kind of cool. Okay, so maybe quick overview again. So we talked about stereo, we talked about structured light, we talked about laser scanning. We did not talk about time of flight, but I want to quickly recap all the other things first, and then I'm going to go to time of flight separately. So if you're talking about the stereo and multi-view, there's passive. They work indoors and outdoors. They rely on features from environment. If you have a wide wall, it doesn't work. Computationally expensive to do feature matching. Structured light, it's active, can map featureless regions, right? Because you have this IR pattern. Often in IR spectrum, fails outdoors, of course, but indoors great. Kinect amazing. Needs very precise calibration between projector and sensor. And laser and LiDAR scanning, typically a small scan line, often slow if you want to have high quality, but it's typically very precise because feature matching becomes very trivial then. So time of flight we haven't talked too much about. Time of flight itself is complicated. It has a lot of other things. I don't want to talk too much about it because it doesn't fit in this whole like reconstruction stuff what we want to do right now. But the idea of time of flight is what I mentioned already. It basically can map featureless regions, often in IR spectrum, fails outdoors. Sensitive to scattering light, that's also an issue, right? If light scatters and comes back at different times, that's not good. They have indirect lighting suddenly. But yeah, time of flight is like looking at phase differences and stuff like this. There's a lot of cool stuff around it. There's very specific lectures. I skipped it for a simple reason because it doesn't have this nice geometric reconstruction what stereo has. Okay. There's a lot of applications and research directions. There's a lot of cool stuff that built on top of these 3D scanners. And all of these research directions is pretty much what we're doing in our research group. This is why I like it so much, and I'm very, very excited about the research there. The good thing is not much is working perfectly yet, so we can still improve on it. So we have still stuff to do as researchers, but there's also a lot of cool things that already work pretty well. So you can do body tracking, that's what the Kinect was originally made for, gesture control, face tracking. So we do a lot of stuff on faces. If you're curious about faces, humans, we're a group to doing this in our research lab. 3D reconstruction, generally we do a lot of stuff. Localization, semantic scene understanding, I mentioned last lecture a lot. VR, AR, fabrication, just showed you a video. And very hot right now, neural rendering is cool, right? We want to do 3D scanning and then kind of capture holograms with that. And many, many more. Self-driving cars is cool, right? I could do this all day. It's amazing. There's a lot of cool stuff coming out of this. Okay. Yeah, so this is roughly the applications of depth sensing. So I would say, actually, let's continue maybe. I know that the lectures are recorded anyway, so this will be a little bit of a longer lecture, but I still wanted to take a bit of a time to talk about camera concepts. And for camera concepts, we're going to talk a little bit about the camera parameters. So we have these intrinsic parameters and extrinsic parameters, right? And this is now mathematically something that you have to actually know, and you have to know how this kind of stuff works. So in the intrinsics, I already mentioned it. We have a focal length, a principal point. These are the main things we need for the intrinsics. There's also skew and distortion parameters. I put this in parentheses because you don't have it always. Most of the time when you're dealing with it, you probably don't deal with it at all. And then we have extrinsic parameters, which is basically 6 degrees of freedom, post-rotation translation. And these define the transformation to the global camera space. So if you're looking at this image here again, what you have is here an image plane, we have a focal plane, and in this camera frame here, we can figure out how to project from the camera 3D space to the image space with the intrinsics. This is what the intrinsic is doing for us, and then the extrinsic go to the world frame. Okay. Often what we also have to do is we have to map between the depth and the color. That's also part of this is one set of extrinsics. So in the Kinect, right, we had this color sensor and we had the depth sensor here. So this also is a rigid transformation between those two. Okay, so camera concept-wise, this is really something you have to know. And I know that some of the stuff is similar to computer graphics, but here in the computer vision area, this is all done a little bit differently. But this is really important that you understand these concepts and understand how to connect these different lectures possibly even together that you're hearing in these areas. So if I'm talking about camera concepts, I'm typically talking about different spaces. So I'm going to have typically a world space. That's my global 3D coordinates frame, right? That's globally defined. Even if I have multiple cameras, I always have to know how to get to this world space. This is my global coordinate system. I have a camera space. That's for each camera, a 3D space that is being spanned by the camera frustum. Then you have screen, pixel, projective space. You can also talk it like this. This is a pixel position and a depth value per pixel. This is our depth image here, right? Our depth image is in screen or pixel coordinates. This is typically what you have in computer vision. In computer graphics, you also have things like normalized device coordinates, like NDCs. In OpenGL, they are between -1 and 1 cubed. In DirectX, they are between -1, 1 squared times 0 and 1 for the depth. These ones are nothing else but normalized versions of the camera space. Right? This is basically device coordinates in camera space, but this is normalized. Okay. I'm not going to go into too much detail here, but if you're taking a graphics lecture, make sure you can connect these NDCs with the respective two things. If not, we can probably skip it for now. But in the big picture, if you want to do research, you probably have to understand these points. But for the sake of this lecture, we mostly need this part right now. There's also a thing what's called model space. So model space is typically a local coordinate frame for a given model within a scene. Meaning that if you have a scene graph in a 3D scene in a video game, you're going to have local coordinate transformations that go from each object to world space. And then from world space, you could go back to camera space. I'm mentioning this is also a graphics term, but it applies to computer vision as well when you're having, let's say, you do semantic scene understanding, you want to detect objects. So each detected object then lives in model space. Right? And these spaces are very important to memorize. You just need to know in a conversation, oh, I compute X, Y, Z in model space, and then I go back to world space, and so on, right? Okay, we talked about the intrinsics. I wanted to reiterate it. I know some of you might know this already, but this is just so important that we have to go over again. So the intrinsic matrix is assuming you have a pinhole camera model, right? We have this little pinhole, and then we have the film at the back, which is basically receiving the input here on the back of the sensor. Right? Same thing what the human eye is doing, well, except the human eye has not a pinhole model. Pinhole model is the infinitesimally smaller aperture size. In practice, that's not quite the case, but this is what we are using in order to model our cameras. So our cameras have a bunch of parameters. It has the focal length, fx and fy. It has the principal point, mx and my, and then there's an axis skew that we don't always need. For the most parts, we don't need it, actually. Most of the time we calibrate it out anyway beforehand, and most of like Kinect or so, they don't have it. Okay, so the focal length is the distance between the pinhole and the image plane, which makes sense, right? That's just basically the camera setting. The principal point center is most of the time, ideally this here is if it's perfectly symmetric, it's often width half and height half. It's not always the case. If the camera is a little bit off, then this is not exactly in the middle of the image, the principal point, right? But this is the camera center. This is the translation offset, so to say. Yeah, and the axis skew is a shear distortion. It's mostly 0, not always, but for the most part, I think in your exercises and so on, you can assume it's mostly 0. Okay. Yeah, focal length, already mentioned, focal length is distance between the pinhole and the filament, i.e. the image plane. The focal length is typically measured in pixels, and the ratio of fx and fy is the aspect ratio, right? So you need that in terms of defining the projection here in 2D. The principal point is also measured in pixels. It's typically mx or my. Sometimes you see people use x0 and y0. I'm not sure why, but for the most part it's mx and my. This is just the center here where this principal point in the middle part from the pinhole goes back here, and this is then the center of the image plane for the most part, if it's a perfect camera. But in practice, it's mechanically, it's not always the exact center, so then it's not always perfectly in the center. Okay. Now, very important, if you're dealing with camera intrinsics, how do you do a projection? So if you are having a point in camera space, that's my point in camera space here right now, that's XC, YC, and ZC. And this C here denotes it's in camera space. So if I take a point in camera space, a 3D point in a three-dimensional camera space, I apply my intrinsic matrix to it, and I just multiply this 3x3 matrix with my 3D point. The result is going to be U and V, that's my pixel coordinates. There will be a 1, and there's going to be ZC. So the depth value in camera space and the depth value after the projection is actually identical. There's no difference here. Now, what is important, since this is multiplied by ZC, you still need the division by the depth value, right? In order to go to the pixel locations, you have to basically go ahead and divide by CC, right? Otherwise, this doesn't work. So yeah, this is our intrinsic matrix, called K right now. This is our camera point, and this is the respective UVs. But if you're just applying the matrix, notice that what you're getting is the depth times U. So in order to get the pixel coordinate, you have to take whatever comes out of this matrix multiplied, divided by C, only then you get the pixel coordinates. So the screen-based projection looks like this, right? By the way, very important function. This is copied out from my code. This is actually computer code from voxel hashing. But this is camera to screen space, right? So you take a 3 position in camera space. It's a float 3. And what you're doing right now is, for the Z, nothing changes. Z stays the same. And for the other position, what you do is you take the camera, the depth camera parameters, the fx, that's the focal plane in x direction, multiplied by the position in x, divided by the position in C, plus the depth camera mx, right? So plus the principal point. And the same you do for y. And again, this is nothing else but applying this matrix multiply. Here, our skew axis is assumed to be 0, but it's already making the division by the Z here. And this is important, otherwise this doesn't work, right? So this is the screen space projection function, and this basically assumes this is typically in meters, and this one is typically in, so the Z here is in meters, but this one is typically in pixels, right? Because why is it in pixels? Because the focal length and the principal point are both in pixels. Inverse projection, if we have a depth map, and this is also a very important function here, if we're having a depth map and we want to go from the screen space of the depth map to camera space, what we're getting is the xy coordinate in pixel space and the depth value. That's a float variable. And now what you do is you just apply the inverse matrix to that. So what you do is you have ux, like the pixel coordinate you have, you just convert the float, right? Minus the principal point, and then you divide it by the the focal length, and you same do for y. But don't forget at the end you still have to multiply by the depth respectively, right? This is important. You don't forget this one. Anyway, so this is the inverse. This is basically going from screen space to camera space, and these are the important two functions for a lot of the things what we're doing, because it gets us from a depth map to 3D coordinates in camera space, or it gets us from camera space back to a depth map. Okay, these are the intrinsics. Let's talk about the extrinsics. So the extrinsics are basically 6 degrees of freedom. So we're having a translation and you're having a rotation. 3 of the degrees of freedom are for the rotation. It's basically 3 angles. if you're in Euler space, and 3 for the translation. Typically, the extrinsic matrix looks like this. It's basically a 4x4 matrix. It has the translation here in the last column. It has a 1 here in the bottom right. It has zeros in these entries, and it has the rotation matrix here. Okay, so that's a 4x4 matrix, or you could also store it as a 3x4 matrix, because this last row is always going to be 0, 0, 1, right? Yeah, so this is our extrinsic, and it has a rotation and a translation part. Now, these are not arbitrary values, these r's here. These are part of a rotation matrix. So a rotation matrix is okay, so this is very interesting. The definition of a rotation matrix is basically that the transpose is equal to the inverse, right? Makes sense. If I rotate in one way, then I take the inverse, just rotate in the other way. So inverse is equal to transpose. That's the definition mathematically of a rotation matrix. And we also need to make sure that the determinant is 1. This is the mathematical definition of a rotation matrix. By the way, if you ever have an interview in these kind of areas, you should know, like, a rotation matrix, okay, inverse is equal transpose, determinant has to be 1. But the rotation matrix you can put together with Euler angles, and you can split it up into 2 separate rotations, right? These 3 rotations here is an x around the x-axis, y-axis, and z-axis, and you have these 3 rotation matrices. I'm aware that most of you know these concepts, but I still wanted to reiterate it because this is so difficult. If you don't know by now what a rotation matrix is, you will have really trouble understanding anything in this lecture in the next part. So please, even if you know it, take a look at it again and really make sure that you understand what rotation matrices are, right? Okay, but the idea is you can stack these rotations, of course, right? So like the final rotation matrix, basically this 3x3 matrix here, has 3 degrees of freedom, has these 3 angles here, these Euler angles, and you're just multiplying the 3 matrices together, and then you're going to get the final rotation matrix, what we actually use. Important here, one thing about extrinsic. Extrinsic is an overloaded term. Extrinsic can mean many things. It's all relative, actually. For instance, if you're talking about cameras, we might have an extrinsic that tells us from one camera to another camera pose to another camera pose. So if the camera is moving or the object is moving, is all relative, right? Does the object move? Does the camera move? It's not clear, right? You don't know. It's all relative. From a matrix perspective, it's the same matrix, right? It's an extrinsic matrix. Same thing actually when you're talking about the extrinsic, that's what I mentioned by overloaded term. Between the depth and the color camera, there's also an extrinsic matrix. Extrinsic matrix, you always have to know from which space you're going. Are you going from camera space to world space? Or are you going between different camera spaces? Or are you going by camera spaces between different frames? Then you call it a pose. Like here, this is a pose because it's between different frames. But if you're going between RGB and depth cameras, then it's between different camera spaces, right? Okay, so I just want to make sure that extrinsic is a bit of an overloaded term, and different people use it differently. But basically, it's a rigid transformation that goes between camera, world space, or different camera spaces, and so on. Okay. Camera calibration. I'm not going to go into all the different camera calibrations, but one of the big problems that we're having, a pinhole camera is not a real camera, right? So a real camera looks like this, that you have a lens, and everything is in focus here in the lens. If you're behind it or in front of it, you have depth of field, so then you have distortions, you have blur. So in real life, this here, not a pinhole camera, right? A lot of distortions, look at this, right? Crazy lens. I have to be aware that there's a lot of different camera models, and there's a lot of way to calibrate these camera models. So for the most part, what we are dealing with is we have 2 types of distortions that we can compensate for. We have radial distortions and we have tangential distortions. So you have different types of cameras, how they distort. Like if you have no distortion, you have a grid, right? You can have negative radial distortion, looks like this. And you can have positive radial distortion, it's a barrel camera, right? Sorry, barrel lens. And this is like how it respectively deforms stuff. So yeah, this is the radial distortion. But then you have the tangential distortion. This is basically on the other plane, right? If you're looking from the side, you have the lens and the sensor are parallel, but in practice, the lens and the sensor are not always parallel, right? This is the problem in the tangential distortion. Okay, So these two are the most common distortions, but I wanted to make very clear, this is again just an approximation. This is not physical, it has a physical model behind it, but a physical camera can have way more different issues. A lens is not always so planar as it is here. A lens can be very complicated, it can be very wrong, can have scratches on it and stuff like this too, right? So camera modeling there's many different versions how to approximate it. This is just one thing that computer vision researchers use often. So if you're talking about camera calibration and have like radial and tangential distortion, you typically optimize for two things. So you typically have camera coefficients. You have this K1, K2, P1, P2, K3. These are basically higher order or polynomials that approximate the respective distortion cameras, right? So typically what you do here, if you look, so if you're taking a radial distortion, you can correct it by taking an input point and multiplying by 1 plus k times k1 times radius squared plus k2 times radius to the power of 4 times radius to the power of 6 and so on. In principle, you can continue these things, right? You can have longer approximations here. This is just one way how to approximate it and what many people do here. Yeah, this is a very common way. It's up to 6th order of the radius here, so that's fine. And for the tangential distortion, if this basically occurs if the image plane and lens are not parallel, I mentioned this in the slide before for the visualization. Here we have these two P parameters here, right? And we can apply them in order to correct it. So maybe these formulas you don't have to memorize by heart, but it's very important that you know that there's basically polynomial approximations of the distortions that we can use then later on to correct it. And then there's tools in the camera calibration tool chain that you can optimize for these distortion parameters, right? And most of the time this works, this is a checkerboard pattern because you can find the detected key points. You know that this is evenly spaced. And based on these ones, you can take a bunch of images. And based on that, you can basically get the calibration right? And this is what people typically do. Opencv has a very good toolbox. If you're interested, just click the link here at the bottom. And then you can do some calibration. Okay. Yeah, this is roughly what we have to know about the cameras in this course. Again, this was a bit of a crash course. I understand that, but I don't want to spend too much time on camera basics. There's a lot more complexity to it than what it is in these slides, right? Because these are all real-world approximations. This is not the actual real world. Okay. Now I wanted to talk a bit about reconstruction. So if we're having intrinsics parameters given, then we can get a point cloud from a current depth frame, right? This is something we can do with a 3D scanner, like a laser scanner, or a Kinect or something like this, right? Now, the one thing, what we haven't talked about is, how do we do actually 3D reconstruction? If you're talking about reconstruction, we can move the camera or the object, either way. Again, it's all relative, doesn't make a difference. Then we get another frame, so we're getting a different viewpoint of the same object. And as part of the 3D reconstruction process, what we have to do now is we have to compute an alignment between these two frames. And this is the pose of the camera, basically. This is essentially an extrinsic, it's a 6 degree of freedom pattern matrix that we have to solve for. This is the alignment problem. So we're computing this alignment in the reconstruction. And then we're having the alignment between those two point clouds. And then we're merging the points. And at the end of the day, we're getting this nice surface. In this nice surface, there's still a lot that I'm not mentioning right now. But I wanted to give you an example in how the cameras are now being used. So the camera intrinsics is the first thing to go from the camera measures to a point cloud. Then you figure out the extrinsics of the current camera position to align the point clouds. And then you merge the point clouds and do some surface reconstruction on top of it. And this is something you can do with many, many views, right? So you have one position, next position, and so on, right? And the idea is that we have many, many poses. And one of the things we're going to deal with in the next few lectures is how do we find the extrinsic alignments? How do we find these poses between the camera frames, these T's? How do we optimize for those? And then finally, how do we get the reconstruction out of it? Cool. So yeah, I know this was a little bit longer as a lecture, but I wanted to still give you a high-level overview of all the 3D concepts. And I hope this gives you already a bit of an intuition in how we can use laser scanners, and hope you're as excited as me in terms of doing cool stuff with it. So a few administrative things. So this week, there's going to be the first tutorial. There's going to be released the first assignment, introduction to the first assignment, and then you have to figure out groups. Check out Moodle. There's going to be all the announcements. Otherwise, thanks a lot for watching the lecture. See you next week. Have fun studying and looking at the exercises.